Let's now explore some applications of standing waves, such as standing waves in a string musical instrument like a guitar. When a guitar string is plucked, then a standing wave is formed as a result of the superposition of waves that reflect back and forth from the ends. The corresponding specific sound is produced in the process, which no matter how many times the same string is plucked, the sound remains the same. Why is that so? Well, this is a direct consequence of the nature of the taut string that always wants to oscillate in specific natural modes of oscillations that are known as natural oscillating frequencies, and they correspond to specific standing wave types. Consider the following demonstration where a stretched string is set to vibrate at a particular frequency to create a standing wave. Notice that the ends of the string are fixed and always have notes because they cannot vibrate. The lowest natural oscillated frequency for a stretched string is known as the fundamental frequency or the first harmonic. The fundamental vibrational mode of a stretched string is such that the wavelength is twice the length of the string. In this case, the standing wave appears to consist of an antinode in the middle of the string and two nodal positions at the locations where the string is fixed, like in the video. The next natural oscillating frequency for a stretched string that produces a standing wave is known as the second harmonic. The second vibrational mode is such that the wavelength is equal to the length of the string. In this case, the standing wave appears to consist of two antinodes at a quarter of the length of the string and at 3/4 of the length of the string. There are three nodal positions at the locations where the string is fixed and right in the middle. The third nodal mode corresponds to the case where the wavelength is 2/3 of the length of the string. In general, the wavelengths of various natural oscillating modes for waves in a medium that have notes at the ends, such as a string fixed at both ends, can be conveniently expressed as the wavelength of the nth harmonic being equal to twice the length of the medium divided by the harmonic number. The harmonic is a positive integer starting from 1. Other examples of such standing waves with fixed ends include sound waves in a pipe that is closed at both ends of the pipe. The natural frequencies associated with these modes of vibration are obtained from the relationship V being equal to F lambda, where V is the wave speed and is the same for all frequencies. We saw that the wave speed of a mechanical wave depends on the properties of the medium through which a wave propagates and is equal to the square root of the force divided by the mass per unit length, or the linear mass density. By combining the harmonic and velocity equations and solving for frequency, it can be shown that the natural frequency of the standing wave is given by f of n is equal to n divided by 2l times the square root of f divided by mu. For the first harmonic, where n is equal to 1, the fundamental frequency is 1 over 2l times the square root of f over mu, which in the case of a guitar string is the frequency of the sound that one hears when the string is plucked once. That frequency can be changed either by varying the tension or by changing the length. That's why a different sound, i.e. a different frequency, is heard when we alter the tension on the guitar string by tightening the string or loosening it. Likewise, a different frequency will be produced every time you place your finger in a different position along the guitar neck. This action changes the length of the vibrating portion of the string and thereby affecting the formula for the frequency. For a given string with a length of 2 meters and a mass per unit length of 0.05 kilograms per meter under a tension of 50 newtons, what is the wavelength of the second harmonic? What is the frequency of the second harmonic? So we've seen that a system, such as a stretched string, is capable of oscillating in one or more natural modes of vibration. If a periodic force is applied to such a system, the resulting amplitude of a wave is larger when the frequency of the applied force is equal to or close to one of the natural frequencies. This matching frequency results in a phenomenon called resonance. As such, the corresponding natural frequencies of oscillation of the system are often referred to as resonant frequencies. Recall back to the last time you were on a swing in a playground. In order to gain maximum height, it is necessary to increase the swinging force. We intuitively know that this is best achieved as long as we exert the necessary force at just the right moment in time, or in other words, at the right frequency. Only then will the motion of the swing result in a higher oscillating amplitude, meaning a higher swing. We want resonance to occur in some applications, such as in musical instruments or on a swing, but at other times, resonance is undesirable and can lead to detrimental effects. On a stretched string, the standing waves can be established at frequencies that correspond to the natural modes of vibration of the string. The natural oscillating frequencies is given by the frequency at the nth harmonic being equal to n divided by 2L times the square root of F divided by mu, where L is a length, F is a force or the tension, and mu is a linear mass density or mass per unit length. The lowest natural frequency, where n is equal to 1, is called the fundamental frequency. The phenomena where a vibrating system or external force drives another system to oscillate with greater amplitude at the natural frequency is known as resonance.